January 14, 2005. The European Space Agency's Mission Control in Darmstadt, Germany. Scientists are crowded around screens, watching data arrive from a spacecraft that has been traveling for 7 years. The spacecraft is called Huygens, a probe, the size of a large beach ball, carried to Saturn by the Cassini orbiter, released 3 weeks earlier, now descending through the atmosphere of a moon that has tantalized astronomers for decades. A moon with a thick orange haze so impenetrable that, until Cassini arrived, nobody had ever seen its surface. Huygens is transmitting as it falls, the data comes back, the scientists process it, and one by one, the revelations arrive. There is an atmosphere, a thick one, dominated by nitrogen just like Earth's, with a surface pressure about 1.5 times that of Earth at sea level. The temperature at the surface is approximately -179 degrees Celsius. There are clouds, there are rivers of something, not water. The temperature is far too cold for that, but rivers, carving channels through a landscape of water ice rock, running downhill toward basins in the lowlands. The surface, when Huygens finally reaches it, is dark and wet, and covered in rounded pebbles of water ice that have clearly been shaped by flowing liquid, shaped by currents, by erosion, by the same physical processes that shape river stones in every river on Earth. Then, the chemical data comes back. The atmosphere is full of organic molecules, complex, carbon-based compounds, assembled from the methane and nitrogen of Titan's air, by ultraviolet light, and the energetic particles of Saturn's magnetosphere. The same kinds of molecules that, 4 billion years ago on early Earth, are thought to have been the precursors from which life eventually assembled itself. The scientists in Darmstadt are not celebrating life on Titan. They are more careful than that. But one of them, looking at the data arriving from a world 1 billion kilometers away, says something that captures exactly what they are all feeling. He says, "This looks like early Earth." And he is right. It does look like early Earth, except for one thing. Titan is the most Earth-like world in the solar system. It has an atmosphere denser than ours. It has weather, clouds, rain, and seasons. It has a complete hydrological cycle, with liquid evaporating from surface seas, forming clouds in the atmosphere, and falling as rain on the land. It has rivers and deltas and lakes and dunes. It has organic chemistry, more complex and more abundant than anywhere else we have ever looked. It has 2 oceans, one of liquid methane on the surface, and one of liquid water beneath the ice, and it has one thing missing, one absence, one gap in the inventory, one ingredient that life, as we know it, cannot do without. The answer to what that missing thing is will surprise almost nobody. The implications of that answer will surprise almost everyone. This video is about Titan, Saturn's largest moon, the second largest moon in the solar system, larger than the planet Mercury. A world so extraordinary that, in the 2 decades since Huygens landed on its surface, it has steadily risen from interesting target to one of the most scientifically important objects in the solar system. Titan has a dense nitrogen atmosphere, the only moon in the solar system with a surface pressure 1.5 times that of Earth at sea level. It has a complete methane cycle. Liquid methane evaporates from its lakes and seas, rises into the atmosphere, forms clouds, falls as rain, and flows back to the seas through rivers and channels, the same cycle that water performs on Earth, but with a different molecule in a world 200 degrees colder. It has organic chemistry that dwarfs anything elsewhere in the solar system. The photochemical reactions in Titan's upper atmosphere convert methane and nitrogen into an enormous variety of complex organic compounds. Tholins, the orange haze particles that give Titan its characteristic color, but also simpler compounds that rain down onto the surface and accumulate in a layer of organic material covering the entire moon. Scientists estimate there is more organic carbon on Titan's surface than in all of Earth's known oil reserves combined. It has a subsurface ocean of liquid water, maintained by the tidal heating generated by Saturn's gravity, sitting beneath a shell of water ice, an ocean world, just like Enceladus, but with a very different surface above it. And it has, as of a paper published in July 2025 in the International Journal of Astrobiology, a proposed mechanism by which protocell-like structures, the precursors to cells, could be forming right now in its methane lakes. The one thing missing from all of this is liquid water at the surface. Water, the solvent in which all known biochemistry occurs, is absent from Titan's surface because the temperature is far too cold. At -179 degrees Celsius, water is a rock, rigid, frozen, as different from a solvent as granite. But here is where the story gets interesting, because Titan's methane and ethane lakes are liquid. They are a solvent. And the question that has been slowly building in the astrobiological literature for 2 decades, and that the July 2025 paper brought to a new level of concreteness, is this. Does life require water specifically? Or does it require a liquid solvent, any liquid solvent, and water is simply the one that life on Earth happened to use? By the end of this video, you will understand exactly what Titan is, what it has, what it lacks, and why the answer to, does life require water, may be the most important scientific question that Dragonfly, launching in 2028 and arriving in 2034, is going to begin to answer. So what exactly does Titan have, and what exactly is missing? Why is Titan's atmosphere more similar to Earth's than any other world in the solar system? And what does that tell us about the conditions under which life might arise? What is a tholin? And why is the orange haze that surrounds Titan one of the most chemically interesting phenomena in the solar system? What is the July 2025 protocell paper actually claiming? And what would it mean if protocell-like structures are forming right now in Titan's methane lakes? What is Dragonfly, and what specific questions is it designed to answer when it arrives at Titan in 2034? And the deepest question of all, does life require water, or does it require only a liquid solvent? And if the latter, could Titan's methane seas be hosting a form of biochemistry so different from ours that we would barely recognize it as life? This is not a video claiming life has been found on Titan. Life has not been found on Titan. We have not sent an instrument capable of detecting life to Titan's surface. The evidence we have comes from Cassini's flyby data and Huygens' 2.5-hour surface transmission, neither of which was designed as a life detection mission. What we have is chemical evidence that Titan has the ingredients. The kitchen is stocked. Whether anyone is cooking remains unknown. But this is also not a video dismissing Titan as an uninhabitable frozen wasteland. The scientific picture of Titan in 2026 is far richer and far more provocative than either the dismissal version or the discovery version. Titan is the most chemically complex world we have yet found beyond Earth. It is the only place in the solar system where the conditions on the surface resemble, in their dynamics, in their liquid-solid gas cycling, in their organic richness, the conditions on early Earth. And it presents, for the first time in the history of astrobiology, a serious scientific case for a form of life that does not use water as its solvent. Whether that life exists is unknown. That it could exist is no longer purely speculative. Stay with me. Before we go deeper, if these are the kinds of stories that pull you in, real planetary science told carefully and honestly, where the almost is as interesting as the yes, hit subscribe. Galaxy Pulse goes beyond the headlines every single time. We will not tell you we found life when we haven't, but we will tell you why Titan might be the most interesting place in the solar system for the question of what life actually is and what it doesn't have to be. Now, back to Titan. and to the world that is almost Earth, except for one thing. To understand why Titan is extraordinary, and why the "except one thing" in this video's title is both the most obvious answer and the most interesting question, we need to start with what Titan actually is. Not just its statistics, its character, because Titan is not simply another icy moon in the outer solar system. It is a world with a biography, with weather, and geology, and chemistry, and possibly, not probably, but possibly, with processes that are beginning to look very much like the first pages of a story that, on Earth, eventually led to us. Saturn is the sixth planet from the Sun, a gas giant 1.4 billion kilometers from Earth at closest approach. Its system of rings and moons is one of the most complex planetary environments in the solar system. 146 confirmed moons, as of the most recent count, ranging from tiny captured asteroids to worlds larger than some planets. Titan is the largest of them. It was discovered by the Dutch astronomer Christian Huygens in 1855. The same Huygens whose name was given to the probe that landed on its surface 350 years later. And for most of those 3.5 centuries, it was known primarily by what it was not a small, airless, cratered rock like most moons. Something larger, something with an atmosphere, something that revealed itself as unusual the moment early spectroscopy showed the presence of methane above its surface in 1944. But what Titan actually was remained largely mysterious until Voyager 1 arrived in 1980. Voyager's cameras showed a globe wrapped completely in a thick, uniform orange haze. No surface features were visible. The haze was not a cloud layer, like Jupiter's visible cloud bands, that spacecraft could see through with the right instruments. It was a photochemical smog. An atmosphere full of complex organic molecules created when solar ultraviolet light and energetic particles from Saturn's magnetosphere broke apart the methane and nitrogen in the upper atmosphere and allowed the fragments to recombine into increasingly complex compounds. The compounds fell out of the upper atmosphere and accumulated on the surface. For decades, scientists speculated about what the surface looked like beneath the haze. Was it a global ocean of liquid hydrocarbons, as some models predicted, a frozen plain, a complex landscape of varied geology? Nobody knew, because nobody could see it. When Cassini arrived at Saturn in 2004, beginning a 13-year mission that would fundamentally transform our understanding of the Saturnian system. It carried instruments specifically designed to see through Titan's haze. Radar, near-infrared cameras tuned to the wavelengths at which the haze is most transparent, and the Huygens probe, designed to enter the atmosphere and transmit data all the way to the surface. What Cassini and Huygens found was not a global ocean. It was something stranger and more interesting. A world with continents and mountains, made of water ice, coated with a layer of dark organic material. Enormous dunes at the equator, composed of organic particles blown by steady winds. River valleys and lake beds, dry in some regions but filled with dark liquid in the polar regions, particularly the North Pole. And at the North Pole, a system of seas and lakes that, in the Cassini radar maps, looked immediately, unmistakably, and disorientingly familiar. They looked like a coastline. Not like the smooth, impact-cratered surfaces of most moons, not like the volcanic plains of Io or the ice-fractured terrain of Europa. They looked like a satellite image of Earth's lake country. Convoluted shorelines, islands, river deltas, bays and inlets, features carved by the same hydraulic processes, erosion, sediment transport, wave action, that shape coastlines everywhere on Earth. Except that the liquid filling these lakes was not water. It was methane. Liquid methane, at -179 degrees Celsius, filling seas that are, in some cases, larger than the Caspian Sea on Earth. Let us sit with that for a moment. On the surface of Saturn's largest moon, right now, there are seas of liquid methane. There are rivers that flow into those seas, carrying dissolved organic compounds from the interior. There are waves, driven by winds, breaking on shorelines that have been shaped by millions of years of hydraulic erosion. There are rainstorms, not water rain, methane rain, that fall on the surface and flow across the landscape. There are methane swamps, and riverbeds, and beaches of organic particles, and dunes of organic sand. The hydrological cycle is complete. Evaporation, cloud formation, precipitation, surface flow, all of it with methane instead of water. It is the most Earth-like surface process anywhere in the solar system, and the atmosphere above all of this is making things. The chemistry in Titan's upper atmosphere, driven by sunlight and particles from Saturn's magnetosphere, is one of the most productive organic synthesis environments known. Methane and nitrogen react to form a cascade of increasingly complex molecules: tholins, amino acid precursors, nitriles, polycyclic aromatic hydrocarbons. These compounds have been detected in Titan's atmosphere by Cassini's mass spectrometer and by spectroscopic observations from Earth. They rain down on the surface, they accumulate, they react. Scientists estimate the total inventory of organic carbon on Titan's surface exceeds the total known organic carbon in all of Earth's known petroleum reserves. Combined, Titan is, by this measure, the most organically rich world in the solar system outside of Earth. But it is missing something. Here is what a habitable world, by the definition we have always used, needs: liquid water, energy, organic chemistry, a stable environment that persists long enough for complexity to build. Titan has 3 of these 4. The organic chemistry, extraordinary, unmatched elsewhere in the solar system, actively being produced at enormous rates by atmospheric photochemistry and accumulating on the surface in quantities that dwarf Earth's reserves. The energy, multiple sources, solar ultraviolet, driving the atmospheric chemistry, albeit weakly at Saturn's distance. Chemical energy, from the reaction of organic compounds with the subsurface water ocean. Tidal heating from Saturn's gravity, maintaining the subsurface liquid water. The stable environment. Titan has maintained its thick atmosphere, its methane lakes, and its surface chemistry over geological timescales, billions of years, almost certainly, during which the basic character of the world has remained broadly similar. What Titan does not have is liquid water at the surface. At -179 degrees Celsius, water is not a liquid. It is a solid, as hard and rigid as granite. The solvent that all known biochemistry uses, the medium in which the chemical reactions of metabolism and replication occur, is absent from Titan's surface. And this is the one thing, the missing ingredient, the gap in an otherwise extraordinary inventory. But here is where the story diverges from the simple version. Because the scientific question, the question that Titan's chemistry has been forcing astrobiologists to take increasingly seriously for 2 decades, is not, does Titan have what life needs? The question is, does life need what Titan doesn't have? Does life need water, specifically? Or does life need a liquid solvent, and water is simply the solvent that life on Earth chose? These 2 questions have very different answers, and Titan is, right now, the most important place in the solar system for the second question. Because, if a solvent other than water can support biochemistry, Titan, with its methane and ethane lakes, its extraordinary organic inventory, and its complex atmospheric chemistry, is the most plausible candidate in our solar system for a world where that different biochemistry might be occurring. The story of how scientists began taking Titan seriously as a possible habitat begins not with life, but with chemistry. In the early 2000s, before Cassini arrived, theorists began asking a specific question: if liquid methane is a stable, permanent feature of Titan's surface, and the evidence from ground-based observations strongly suggested it was, Then what would life look like if it existed there? Not water-based life transplanted to Titan. Life that arose in methane. Life whose biochemistry was organized around a hydrocarbon solvent instead of a water solvent. The question is harder than it sounds. Water is a nearly perfect solvent for biochemistry for reasons that are deeply connected to its molecular structure. Water is polar. It has a slight positive charge on the hydrogen end and a slight negative charge on the oxygen end. This polarity makes it excellent at dissolving other polar and ionic molecules, including the amino acids, nucleic acids, and salts that life's chemistry depends on. Water forms hydrogen bonds, which give it extraordinary properties: high surface tension, high heat capacity, the anomalous expansion upon freezing that makes ice float. All of these properties turn out to be deeply important for the specific chemistry of known life. Methane has none of these properties. It is nonpolar. It does not form hydrogen bonds. It is a much poorer solvent for the kinds of molecules that Earth life uses. But what if life in methane used a different set of molecules? In 2015, a pair of theorists at Cornell University, James Stevenson, Jonathan Lunine, and Paulette Clancy, published a paper proposing a hypothetical cell membrane that could exist in liquid methane. On Earth, cell membranes are made of phospholipids, molecules with a water-loving head and a water-fearing tail that spontaneously assemble into double-layer membranes in water. In methane, you would need the opposite, molecules with a methane-loving tail and a methane-fearing head. The theorists called their proposed structure an azotosome. They calculated that it would be thermodynamically stable in liquid methane at Titan's temperatures and would have mechanical properties comparable to Earth's phospholipid membranes. The azotosome was a hypothetical construct, a thought experiment, but it demonstrated, for the first time with quantitative rigor, that a cell-like structure could in principle exist in Titan's methane without requiring any of the molecular machinery that Earth life uses. Then, Cassini began returning data. The mass spectrometer aboard Cassini, flying through Titan's upper atmosphere on numerous close flybys, detected an extraordinary range of organic compounds, far more complex than anyone had anticipated. By the mission's end, hundreds of distinct compounds had been identified, including molecules that, on Earth, are precursors to amino acids and nucleic acid bases. The atmosphere was not just producing simple hydrocarbons, it was assembling the molecular alphabet of prebiotic chemistry. Then came a subtler observation that generated intense scientific discussion. In 2010, researchers analyzing Cassini data found that the distribution of hydrogen near Titan's surface showed a depletion, less molecular hydrogen in the lower atmosphere and at the surface than models predicted. In 2010, another analysis found that acetylene, which should accumulate on Titan's surface from atmospheric production, was depleted relative to predictions. Both depletions were consistent, though not uniquely explained, by a hypothesis that something on the surface was consuming hydrogen and acetylene. If life existed in Titan's methane lakes, it would need an energy source. One plausible metabolic pathway, proposed theoretically, would involve combining acetylene with hydrogen to release energy, analogous to how oxygen-breathing life on Earth combines oxygen with organic compounds. The specific signature of such metabolism would be depletion of hydrogen and acetylene at the surface. The Cassini data showed exactly that depletion. This was not confirmation of life. Chris McKay, who published the original theoretical paper proposing the acetylene metabolism, was explicit. The depletions could have abiotic explanations. They were interesting. They were not proof. But they were the beginning of a pattern, a world that kept producing data consistent with the possibility of biology, not confirming it, just being consistent with it. Then came September 2025. A team, led by Grace Richards at the Europlanet Science Congress in Helsinki, presented experimental results showing that organic molecules in Titan's plumes, wait, those are Enceladus, on Titan itself. In July 2025, a paper by Christian Mayer and Connor A. Nixon, in the International Journal of Astrobiology, proposed a specific mechanism by which protocell-like structures could be forming in Titan's methane lakes right now. The mechanism involves amphiphilic molecules, molecules with both methane-loving and methane-fearing parts, that naturally accumulate at the interface between the methane liquid and the atmosphere. Wave action on the lake's surface would generate droplets. When those droplets fell back to the methane surface, the amphiphile layer would encapsulate them as bilayer vesicles, membrane-bounded droplets, in methane lakes, from organic chemistry produced in the atmosphere, protocells, not life, but the structure that, on Earth, is thought to be one of the earliest stages in the origin of life. The enclosure of chemistry within a membrane boundary that allows concentration and eventually evolution might be forming spontaneously in Titan's seas. Let us make the key science here concrete, because several things in Titan's story require a bit of unpacking to appreciate fully. Think of it this way. Imagine you wanted to build a city. You have all the building materials: steel, glass, concrete, wood, wiring. You have the energy to build, electricity, fuel, human labor. You have the plans, the designs, the accumulated knowledge. But you don't have water, not for drinking or for washing, for chemistry, for the specific medium in which all the biochemistry of the builder's bodies occurs. Without liquid water at the right temperature and pressure, the builders cannot function. That is Titan. Everything is there for the building. The materials are extraordinary. The energy sources are real. The chemistry is astonishing in its complexity and abundance. But at the surface, the specific medium in which Earth-type biochemistry operates is absent. Now, imagine an alternative. What if the builders could function not in water, but in something else? What if there was a different medium, methane, say, that could support a different but equally valid kind of chemistry? Different molecules, different reactions, different cellular architecture, but the same fundamental logic. Capture energy from the environment, use it to maintain a chemical disequilibrium inside a membrane boundary, reproduce. That alternative is what the azotosome hypothesis and the protocell paper are suggesting. There are three concepts essential to understanding this. The first is what a solvent does in biochemistry. A solvent is the medium in which chemical reactions occur. In water-based life, water dissolves the molecules involved in metabolism, DNA replication, protein synthesis, and every other biochemical process. The polarity of water, the slight electrical imbalance in its molecule, is what makes it such a good solvent for the kinds of molecules life uses. Take water away, and those reactions cannot occur. In methane-based life, a different solvent would dissolve different molecules and support different reactions. The molecules would be nonpolar, electrically neutral, without the charges that water-based life's molecules carry. The reactions would occur at extremely low temperatures. The metabolic energy sources would be different. But the fundamental requirement, that chemistry be organized inside a membrane boundary that allows information to accumulate and be replicated, is a geometric and thermodynamic requirement that methane can potentially satisfy. The second concept is what tholins are and why they matter. Tholins are the complex organic compounds produced in Titan's atmosphere, reddish-brown solid particles that give the moon its characteristic color and rain down on the surface continuously. The name was coined by Carl Sagan and Bishan Carr in 1979 to describe a class of compounds that had no simple name in chemistry at the time. complex, heterogeneous, nitrogen-containing organic materials produced by radiation chemistry in reducing atmospheres. When tholins from Titan's simulated atmosphere are dissolved in water in laboratory experiments, they produce amino acids, nucleobases, and other biomolecules. They are, in a very real sense, the pre-cooked ingredients of life, complex organics ready to be assembled into more complex structures given the right conditions. On Titan, those tholins are present in enormous quantities on the surface, in the atmosphere, and in the lakes. They are not being dissolved in water, but they are being dissolved in methane and ethane, solvents that support different chemistry that is only beginning to be characterized. The third concept is the Selk crater, Dragonfly's primary landing site, and why it matters. Selk crater is an impact crater approximately 80 kilometers across, located in Titan's equatorial region. Impact craters on Titan are scientifically valuable for a specific reason. When a meteor strikes Titan's icy surface, the impact heat momentarily melts the water ice, creating a temporary pool of liquid water on the surface. For thousands to tens of thousands of years after a large impact, liquid water persists in and around the crater before refreezing. During that window, brief by geological standards, but long by chemical standards, water-based chemistry can occur. The tholins on the surface dissolve in the water, complex molecules react, amino acids, nucleobases, and other prebiotic compounds form. Then the water freezes again, and the products of those reactions are preserved in the ice. Selk crater is not currently active. The water has long since frozen. But the chemical products of the impact-driven water chemistry may be preserved in the crater's floor, waiting to be sampled by Dragonfly. When Dragonfly arrives in 2034 and analyzes the material in Selk crater, it will be, in effect, reading the output of a natural laboratory experiment in prebiotic chemistry, an experiment that ran in Titan's distant past and whose results have been frozen in place. Here is where the stakes rise in a way that goes beyond Titan itself. If life exists on Titan, in any form, using any chemistry, it would be the second independent origin of life in the history of our solar system. Not life descended from Earth through panspermia. Not life related to us in any way. A completely independent origin, using completely different chemistry, in a completely different solvent, at a completely different temperature. The implications would be transformative. One origin of life could be a cosmic accident, a freak occurrence, possible only under the specific conditions that existed on early Earth, unlikely to be repeated elsewhere. If life arose only once in the entire history of our solar system, on Earth, and nowhere else, then the universe might be nearly empty of life. The silence of the cosmos would make sense. We might be the only ones. Two independent origins of life in the same solar system would suggest something very different. That life is not an accident. That it is a consequence, something that chemistry does, given sufficient time and sufficient organic complexity, in liquids, wherever it can. That the universe is not empty. That everywhere there are planets and moons with liquid solvents and organic chemistry and energy, which, it turns out, is many places. Life is probably doing something. One origin means the cosmos is probably silent. Two origins means the cosmos is probably teeming. Titan is the test case, not the confirmed result. The test. And that test. Dragonfly's exploration of whether Titan's chemistry has crossed the threshold from prebiology to biology, in either the methane lakes or the subsurface water ocean, may be the most important scientific mission of the 21st century. The stakes are clear. The chemistry is extraordinary. The mechanisms, azotosomes, protocells, tholin chemistry, methane metabolism, are theoretically coherent, but none of them have been observed. Dragonfly launches in 2028. It arrives in 2034, and what it will find when it samples the surface of Titan, whether the organic chemistry has produced anything that could be called a biosignature, whether the tholin-rich surface preserves any evidence of biological processes, whether the methane lakes contain anything that is not chemistry alone, remains completely unknown. In the meantime, there is another layer to Titan's story that is separate from the methane lake question entirely. Because beneath the icy crust, beneath the organic surface, beneath everything that Cassini saw, there is a liquid water ocean, and that ocean is not a theoretical inference. It is confirmed. And what it means for Titan's habitability, for the possibility of a second kind of life, in a second kind of environment on the same world, is a question that the methane lake story has almost completely overshadowed. Titan is not one world, it is two. On the surface, the methane chemistry world, the lakes and rivers and organic dunes and photochemical atmosphere, the world that Huygens landed on and Cassini mapped, the world that Dragonfly will explore. Beneath the surface, a water ocean, liquid, global, salty, deep, a world more similar to Europa or Enceladus than to the icy methane world above it. The evidence for Titan's subsurface ocean came from Cassini in a beautifully indirect way. Titan is tidally locked to Saturn. It always shows the same face to the planet, as the Moon does to Earth. Saturn's gravity exerts an enormous tidal force on Titan, deforming it slightly as it orbits. If Titan were rigid, a solid ball of ice, the deformation would be small and predictable. But Cassini's measurements of Titan's gravitational field showed that the Moon deformed significantly more than a solid body would. The most natural explanation for the enhanced tidal deformation is a global layer of liquid beneath the ice. Liquid that can flow and redistribute itself as Titan's orbital position changes, allowing much larger deformation than a solid interior would permit. The subsurface ocean is probably 100 to 200 kilometers deep. It sits beneath an ice shell, perhaps 50 to 100 kilometers thick. It is almost certainly salty, high in ammonia and other dissolved compounds, which lowers its freezing point and keeps it liquid despite the cold temperatures, and it is in contact with a rocky core. This last point is crucial for the question of habitability. Enceladus has a subsurface ocean in contact with a rocky core, and the hydrothermal activity at that core-ocean interface is what makes Enceladus so exciting for life. The mixing of hot rock chemistry with liquid water provides both the chemical energy and the molecular complexity that could support biology. Titan's situation is broadly similar. The rocky core beneath the water ocean is being heated by tidal friction and by the slow cooling of radiogenic isotopes. The water at the base of the ocean is in contact with this rocky core. Hot water plus rock equals hydrothermal chemistry, the same chemistry that drives seafloor hydrothermal systems on Earth. The same chemistry that some researchers believe produced the conditions in which life first arose on our planet. Titan's subsurface ocean may be a hydrothermal system. If it is, it has all three of the ingredients that astrobiologists identify as necessary for life: liquid water, chemical energy from hydrothermal reactions, and organic compounds that percolate down from the surface through the ice shell. The April 2025 biomass study by Antoine Holder and colleagues modeled this scenario quantitatively, asking how much life a Titan-like subsurface ocean could sustain given the available chemical energy and organic inputs. Their conclusion, that Titan could harbor life, but only a tiny amount, constrained by the limited percolation of organic compounds through the thick ice shell, was carefully framed as an upper bound, not a detection. But it demonstrated something important. The habitability case for Titan's subsurface ocean is not based on speculation. It is based on real physics and real chemistry applied to real measurements. The subsurface ocean makes Titan a double candidate. Two environments, two possible habitats, two possible chemistries, The methane lakes on the surface, where a radically exotic form of life might use methane as its solvent, and the subsurface water ocean, where something more like enceladus-type biology might exist in a more familiar aqueous environment. Titan is not just almost habitable, it is possibly doubly habitable, in two completely different ways, by two completely different kinds of life. The Methane Thick Crust Study, published in October 2024, which revealed that methane gas may be trapped within the icy surface of Titan, forming a distinct crust up to 6 miles thick, adds another layer. This insulating crust warms the underlying ice shell and likely helps maintain the subsurface ocean. The methane that makes the surface chemistry so extraordinary is also, it turns out, one of the mechanisms keeping the water ocean below liquid. The surface chemistry and the subsurface ocean are not independent. They are connected. The same moon is running two separate experiments in the chemistry of life, one exotic and one familiar, simultaneously. There is a way of looking at Titan that is both scientifically precise and philosophically startling. Titan's atmosphere today looks like Earth's atmosphere looked approximately 4 billion years ago. Early Earth had no free oxygen. Photosynthesis had not yet evolved to produce it. The atmosphere was dominated by nitrogen, with methane and carbon dioxide as the main trace gases, and with the energy of lightning, ultraviolet radiation, and volcanic activity, driving the synthesis of complex organic molecules from these simpler ingredients. This is the environment that Stanley Miller and Harold Urey simulated in their famous 1953 experiment. A flask of nitrogen, methane, water, and hydrogen, with a spark for energy, that produced amino acids within a week. The Miller-Urey experiment demonstrated that organic chemistry arises spontaneously in reducing atmospheres given sufficient energy. It was the first direct evidence that the building blocks of life could form from simple inorganic precursors. Titan is running a version of the Miller-Urey experiment at planetary scale, in real time, right now. The ultraviolet light from the sun and the energetic particles from Saturn's magnetosphere drive the same kinds of reactions that Miller and Urey simulated in their flask. But instead of a flask, the reactor is an atmosphere, 5 times denser than Earth's, surrounding a moon larger than Mercury, with 4 billion years of uninterrupted operation. The products are tholins. The name, as noted, was coined by Carl Sagan, who was one of the first scientists to take Titan's chemistry seriously as a model for early Earth. Tholins are not a single compound. They are a family of compounds, complex, heterogeneous, orange-brown solids, whose exact composition varies depending on the specific mixture of starting gases and the type of energy driving the synthesis. Cassini's instruments identified hundreds of distinct molecules in Titan's atmospheric chemistry, including many that are direct precursors to biological molecules. The specific connections are worth stating explicitly. In laboratory experiments where tholins are produced from nitrogen-methane mixtures, essentially simulating Titan's atmospheric chemistry, the products include glycine, the simplest amino acid, adenine, one of the 4 bases of DNA, cytosine, another nucleobase, uracil, a nucleobase of RNA. The organic chemistry of Titan's atmosphere is not just producing random carbon compounds. It is producing, in meaningful abundance, the specific molecules that life on Earth is built from. It is not producing life. It is producing life's alphabet. And then, it is raining that alphabet down onto the surface of Titan, where it accumulates in an organic layer of extraordinary depth and complexity, dissolves partially into the methane lakes, and, under the right conditions, such as a meteorite impact that briefly creates liquid water, might be assembling itself into something more. Here is a detail that is worth sitting with. The tholins on Titan's surface are there right now. They have been accumulating for billions of years. The layer of organic material on Titan's surface is estimated to be meters thick in some regions. A global sedimentary deposit of prebiotic chemistry that has been building since long before Earth's first cells appeared. When Huygens landed in 2005, it landed in this stuff. The surface it touched was dark and slightly sticky, a mixture of water ice and tholins, coated with organic particles that had been falling from the sky since Titan's atmosphere first formed. If you could scoop up a handful of Titan's surface and dissolve it in water, something that may have happened at Selk Crater, when the impact melted the surface ice, you would get a solution containing amino acids, nucleobases, and the molecular ingredients of life. Not life itself, the ingredients, the recipe, waiting for the right conditions. The October 2024 methane-rich crust study added another dimension to this picture. The methane gas trapped in Titan's icy crust, forming a distinct insulating layer up to 6 miles thick, means that the organic material on the surface is sitting on top of a thermally insulated foundation. The crust is warmer than it would otherwise be. The chemistry in the organic layer is occurring in a slightly more favorable thermal environment. The July 2025 protocell paper represents the latest step in this chain of reasoning. Mayer and Nixon proposed that amphiphilic molecules, organic compounds with both methane-loving and methane-fearing ends, which could be produced by Titan's atmospheric chemistry, would naturally accumulate at the surface of the methane lakes, forming a thin molecular layer at the liquid-air interface. When waves agitate the surface, droplets are thrown into the air. When those droplets fall back to the methane surface, the amphiphile layer wraps around them. The result is a bilayer vesicle, a membrane-bounded droplet in liquid methane, structurally analogous to a cell membrane in water. This is not life. A vesicle is not alive. But the enclosure of chemistry inside a membrane boundary is, in most origin of life frameworks, a crucial step in the emergence of biological complexity from prebiotic chemistry. The ability of a solvent, even methane, to spontaneously produce membrane-bounded compartments suggests that Titan's chemistry is progressing further along the path toward biological organization than purely abiotic chemistry would be expected to reach. The research is early. The mechanism is proposed, not confirmed. Observational evidence for amphiphilic molecules or vesicle-like structures in Titan's lakes does not yet exist. But the trajectory of the science is clear. With every new analysis of Cassini data, with every new laboratory experiment on tholin chemistry, with every new theoretical model of Titan's surface processes, the case that Titan is not just a chemical curiosity, but a serious candidate for extraterrestrial life has gotten stronger. In 2028, a spacecraft will leave Earth. It will travel for 6 years, covering roughly 1.4 billion kilometers, navigating the interplanetary trajectory that brings it to Saturn's system, and then into the gravitational influence of Titan. It will enter Titan's atmosphere on a heat shield, decelerating from interplanetary velocity to terminal velocity in the thick nitrogen air. It will deploy a set of rotors, and then it will fly. Dragonfly is unlike any planetary mission ever attempted. It is a rotorcraft, 8 rotor blades arranged in 4 pairs, providing lift in Titan's thick atmosphere and low gravity, with a vehicle mass of approximately 450 kilograms. It is nuclear-powered, using a radioisotope thermoelectric generator to provide continuous electricity regardless of lighting conditions. It is a flying science laboratory, capable of covering distances of up to 8 kilometers per flight, and a total surface distance that dwarfs any previous planetary lander or rover. The comparison to previous missions helps put this in perspective. The Mars rovers, Curiosity and Perseverance, are extraordinary scientific instruments, but they can cover at most a few hundred meters per day on rough terrain. Over their multi-year missions, they have traveled tens of kilometers. Dragonfly, flying through Titan's air, will cover comparable distances in a single flight. By the end of its primary mission, Dragonfly will have visited more than 24 distinct sites on Titan's surface, from the equatorial dune fields, to the icy terrain of the mid-latitudes, to the final destination at Selk Crater. At each site, it will land, sample the surface and near-surface material, and analyze the chemistry with its onboard instruments. The science package is comprehensive. The Dragonfly mass spectrometer will identify the chemical composition of surface and atmospheric samples with the sensitivity to detect complex organic molecules, amino acids, and nucleobases, if they are present. The gamma ray and neutron spectrometer will determine the elemental composition of surface materials to a depth of several meters, without requiring sample collection. The meteorology and atmospheric and surface sensors package will measure atmospheric conditions and surface properties at each landing site. And a seismometer will listen for Titan's internal activity, providing the first direct measurements of what is happening in the ice shell and possibly in the subsurface ocean. Selk Crater is the mission's primary science target, and it is worth understanding why. When a meteorite hits Titan, several things happen in rapid succession. The impact vaporizes both the impactor and a significant volume of Titan's icy surface. The vapor, at temperatures of thousands of degrees, expands and recondenses within seconds. But in the immediate aftermath of the impact, as the vapor cools and the crater forms, liquid water pools in the base of the crater and the surrounding area. The heat of impact has melted the water ice that makes up Titan's crust. For a brief period, estimates range from hundreds to tens of thousands of years, depending on the crater size and thermal modeling. Liquid water is present on Titan's surface. During this period, the tholins and other organic compounds on Titan's surface dissolve in the water. Hydrolysis reactions break down complex organic molecules into their components. Synthesis reactions assemble new ones. The specific reaction conditions, moderately hot, liquid water, dissolved organics, with time, are analogous to the conditions that origin of life researchers propose for early Earth's prebiotic chemistry. Then, the water freezes. The products of the chemistry are preserved in the ice. A 2025 paper on amino acid synthesis in Selk Crater, modeling the specific thermodynamic conditions at Dragonfly's landing site, found that the transient liquid water environment created by the impact would have been thermodynamically favorable for the synthesis of amino acids from tholin precursors. The products of that synthesis would be preserved in the crater's floor. Dragonfly's instruments are sensitive enough to detect them. When Dragonfly reaches Selk Crater, it will be reading the preserved record of a chemistry that ran in liquid water, under conditions favorable for prebiotic synthesis, in Titan's past. Whether it will find life, or the products of life, or just chemistry, that is unknown. But here is what is certain. No mission of comparable scientific ambition, designed to directly probe the prebiotic chemistry and potential habitability of a complex organic world, has ever been attempted. When Dragonfly lands on Titan in 2034, it will be the most sophisticated exploration of a potentially habitable world in the history of planetary science. The results, whatever they are, will change what we know. There are three ways to interpret what Titan's chemistry and structure mean for the possibility of life. They sit on a ladder, from the most conservative to the most bold. Each is held by serious researchers, each has supporting evidence, and none will be decisively resolved until Dragonfly returns data from the surface. The conservative interpretation is that Titan is a fascinating prebiotic laboratory, but the conditions for life are insufficient. In this view, Titan's methane lakes are too cold for complex chemistry to be productive. The lack of liquid water at the surface means that the specific reactions that assembled life on Earth, reactions that require water as both a reactant and a solvent, cannot occur in the methane environment. The subsurface ocean, while potentially habitable, is isolated from the rich organic surface chemistry by a thick ice shell, limiting the flux of organic material to the liquid water below. The probability of life is low. The supporting evidence. The extreme cold of the surface, -179 degrees C. The thermodynamic constraints on reaction rates at cryogenic temperatures. The modeling results suggesting that organic percolation to the subsurface ocean is limited by the ice shell thickness. The weakness. This view assumes that known biochemistry is the only kind of biochemistry. It rules out methane-based life, not because of evidence against it, but because of the absence of a detailed mechanism for it. The azotosome and protocell work suggests that the absence of mechanism was a gap in our knowledge, not a gap in nature. The moderate interpretation is that Titan likely hosts prebiotic chemistry at or near the origin of life threshold, and possibly microbial life in the subsurface ocean. In this view, the extraordinary organic richness of Titan's surface, combined with the transient liquid water environments created by meteor impacts and possibly by cryovolcanism, means that prebiotic chemistry on Titan has been running for billions of years under conditions that could have produced the transition to biology. The subsurface ocean, with hydrothermal circulation and a supply of organic material from above, is a plausible habitat for microbial life analogous to Earth's chemolithotrophic bacteria. The supporting evidence. The Upholder biomass modeling, the impact chemistry studies, the methane insulating crust finding, the amino acid synthesis predictions for Selk crater. The biomass study finds that small but non-zero amounts of life in the subsurface ocean are physically possible. The weakness. No direct evidence for life exists. The model makes predictions that dragonfly may or may not be able to test directly. The subsurface ocean is inaccessible to a surface mission. The bold interpretation is that Titan may harbor a second form of life in its methane lakes, a life that does not use water, whose chemistry we do not yet understand, and whose detection will require instruments and frameworks that do not yet exist. In this view, the azotosome and protocell work, combined with the hydrogen and acetylene depletions observed by Cassini, suggest that something in Titan's methane lakes is organizing chemistry in a biological or protobiological way. The specific theoretical mechanisms are developed enough to constitute a falsifiable hypothesis. Dragonfly, while not designed as a life detection mission, may encounter material that is inconsistent with purely abiotic chemistry. The supporting evidence. The Cassini hydrogen and acetylene depletions, the azotosome theoretical work, the July 2025 protocell proposal, the extraordinary organic richness of the surface, the convergence of multiple independent lines of reasoning, all pointing toward the plausibility of methane-based life. The weakness. This view requires life to have solved, from scratch, the problem of building biochemistry in a cryogenic, nonpolar solvent, a problem that, to our knowledge, no known chemistry has solved. The convergent, circumstantial evidence is interesting, but not yet compelling. Dragonfly may find purely abiotic explanations for every anomaly. Here is what is worth saying before we leave the theoretical landscape. Titan has forced a question that astrobiology did not take seriously enough before Cassini. Is water special? Or is it one of several possible solvents for life? On Earth, we cannot answer this question. Every form of life we have ever found uses water. The sample size is 1. We cannot tell whether water is a universal requirement of life, or a historical accident of the conditions on early Earth. Titan is the most plausible place in the solar system where we might find an answer. Not because life on Titan is confirmed or even probable, But, because the chemistry there is sufficiently rich, sufficiently complex, and sufficiently organized in ways we do not fully understand, that the question deserves a direct look. And Dragonfly will give us that look. The most important word in astrobiology right now is not discovery, it is not confirmed. It is falsifiable. Titan's methane life hypothesis is falsifiable. Dragonfly will be there to test it. And whatever it finds, life or chemistry, or something in between, will change what we know about the conditions under which life can arise. After everything we have seen, the methane lakes, the organic atmosphere, the subsurface ocean, the tholins, the protocell proposal, the azotosome, the Selk crater chemistry, the question is no longer whether Titan deserves scientific attention as a potential habitat. It deserves extraordinary attention. The question is what Dragonfly will find when it arrives, and what that finding will mean for one of the oldest and most profound questions in science. And here is where the story takes a turn that most coverage has never gotten. 2. Remember what we asked at the start of this video. What exactly does Titan have, and what is the one thing missing? And why does that missing thing matter less than we assumed? After tracing this story from Huygens' January 2005 landing, through the methane lakes and rivers and organic atmosphere, through the tholins and their connection to early Earth chemistry, through the azotosome and protocell proposals, through the subsurface water ocean and its hydrothermal potential, through the Selk crater impact chemistry, through the three interpretations of what Titan's chemistry means, here is what we now know. And, just as importantly, here is what we still do not. We know Titan has a nitrogen-rich atmosphere, a complete methane hydrological cycle, surface seas of liquid hydrocarbons, extraordinary organic chemistry accumulating on the surface for billions of years, and a confirmed subsurface liquid water ocean. All confirmed by Cassini-Huygens. We know the organic compounds in Titan's atmosphere include precursors to amino acids and nucleobases, that tholins dissolved in liquid water produce biological molecules, and that the impact chemistry at Selk crater would have been favorable for prebiotic synthesis, confirmed by laboratory experiments and modeling. We know that in July 2025, a specific mechanism was proposed by which protocell-like structures could be forming spontaneously in Titan's methane lakes right now. We do not know whether life exists on Titan, in the methane lakes, in the subsurface ocean, or anywhere. No life detection instrument has visited the surface. We do not know whether methane can support biochemistry. The azotosome and protocell proposals are theoretical. Dragonfly will begin to answer these questions in 2034. That is where the science currently sits. Here is the strange thing about how Titan has been covered in popular science media. The coverage exists in a pattern that is both consistent and consistently incomplete. Every few years, a new Cassini result emerges, or a new theoretical paper appears, and a wave of articles appears describing Titan as possibly habitable, or a place where life might exist. These articles typically focus on one specific result, the methane lakes, or the organic atmosphere, or the hydrogen depletion, and present it as new and exciting, which it is, without placing it in the context of everything else that has been found. The result is that the public has a vague impression that Titan might have life, without any clear understanding of why the case has been building steadily for 2 decades, what specifically makes Titan extraordinary, and what the real scientific debates are. Here are the specific things that popular coverage has consistently missed. The first is the double-world nature of Titan. Almost all popular coverage of Titan focuses on either the methane surface or the subsurface ocean, rarely both. The fact that Titan may host 2 completely different potential habitats, operating on completely different chemistry, in one world, is one of the most extraordinary aspects of the Titan story, and is almost never communicated clearly. The methane lakes might host methane-based life. The subsurface ocean might host water-based life. These are independent possibilities that together make Titan's habitability case far stronger than either alone. The second is the connection to early Earth. The fact that Titan's atmosphere is a living, operating analog for early Earth's prebiotic chemistry, that the same reactions that Miller and Urey ran in a flask in 1953 are occurring at planetary scale on Titan right now, is perhaps the most scientifically important aspect of the Titan story, and it is almost entirely absent from popular coverage. Understanding what Titan's chemistry produces is not just relevant to the question of life on Titan. It is relevant to the question of how life arose on Earth. Titan is a natural laboratory for origin of life chemistry that we cannot access on our own planet, because 4 billion years of biological activity have erased the prebiotic record. The third is the July 2025 protocell paper. The Mayer and Nixon paper, proposing a specific mechanism for protocell-like structure formation in Titan's methane lakes, received modest science coverage and has not entered the popular science conversation at anything approaching the level it deserves. A peer-reviewed, quantitative proposal for a specific process by which membrane-bounded droplets, the structural precursors to cells, could be forming spontaneously in the methane lakes of another world right now is a significant scientific result. It was published in a reputable peer-reviewed journal. It deserves wider attention. The fourth is what the Cassini hydrogen and acetylene depletions actually mean, and what they actually do not mean. The 2010 reports of hydrogen and acetylene depletions at Titan's surface generated substantial media coverage framed as a possible sign of life on Titan. That framing, while not entirely wrong, was premature and somewhat irresponsible. The depletions are real. They are consistent with a specific metabolic hypothesis. They are also consistent with abiotic explanations that have not been ruled out. Popular coverage at the time swung between life confirmed and scientists debunked alien life claims without ever settling on the accurate middle position. These depletions are genuinely interesting, consistent with but not proof of biological activity, and a specific data point that Dragonfly's measurements may eventually help interpret. The fifth is what Dragonfly is actually going to do and why it matters. Dragonfly coverage tends to focus on the engineering achievement, a flying drone on another world, rather than on the scientific questions it is designed to answer. The specific question of whether cell craters preserved impact chemistry, contains amino acids, nucleobases, or other biosignature-adjacent molecules is almost never discussed. The specific question of whether any of Dragonfly's chemical measurements will be inconsistent with purely abiotic processes, the operational definition of a positive biosignature result, is rarely explained. Without this context, the public has no framework for understanding what Dragonfly finding something interesting would actually mean. In the period since the July 2025 protocell paper, the scientific picture of Titan's habitability has continued to develop in ways that have not yet fully entered public awareness. The first development is the October 2024 methane-rich crust study. A team analyzing Cassini gravity and radar data published a study in October 2020 for revealing that methane gas may be trapped within the icy surface of Titan, forming a distinct crust up to 6 miles thick. This methane-rich crust acts as an insulating layer, significantly warming the underlying ice shell. The thermal implications are important. A warmer ice shell means a more dynamic interface between the surface organic material and the underlying water ice, potentially facilitating the percolation of organic compounds toward the subsurface ocean. This is a recent result with significant implications that have not yet been fully integrated into the broader Titan habitability picture. A warmer ice shell is a more permeable one. More permeable means more organic material reaching the subsurface water. More organics in the subsurface water means better conditions for the kind of biochemistry that the April 2025 biomass modeling was studying. The second development is the amino acid synthesis modeling for Selk crater. The 2025 paper on prebiotic chemistry in Selk crater, which modeled the thermodynamic conditions during and after the impact, found that the transient liquid water environment was specifically favorable for glycine synthesis from tholin precursors. Glycine is the simplest amino acid. Its presence at Selk crater, if Dragonfly detects it, would be consistent with the impact chemistry model. Its absence, if Dragonfly finds none, would constrain the reaction conditions and help rule out some classes of prebiotic chemistry. Either result is informative. Either result advances the science. The significance of having a specific, quantitative prediction that Dragonfly can test. A falsifiable hypothesis about what the surface chemistry at Selk crater should contain is that Dragonfly becomes not just an exploration mission, but a theory testing mission. The third development is in Dragonfly's mission planning. NASA's Dragonfly mission passed a major milestone in 2024, completing its preliminary design review and confirming the basic architecture of the spacecraft and science payload. The mission is on track for a 2028 launch, using a Space Launch System, or equivalent vehicle, with arrival at Titan in 2034. The science team has been refining the flight plan, identifying the specific landing sites and the sequence in which they will be visited. The Dragonfly mission team published an updated science plan in 2025 that specifically incorporates the most recent results from Cassini data analysis and from laboratory studies of tholin chemistry. The plan emphasizes the prebiotic chemistry goals: amino acid detection, nucleobase detection, complex organic mapping, as primary scientific objectives, alongside the atmospheric and geophysical measurements. The fourth development is in the broader Saturn system context. Enceladus, Saturn's other ocean moon, has continued to be studied intensively. A paper, published in September 2025 at the Europlanet Science Congress, reported new evidence of complex organic molecules in fresh ice grains from Enceladus's plumes, strengthening the case for active hydrothermal chemistry in that moon's subsurface ocean. The relevance to Titan is indirect, but real. Enceladus and Titan share the same solar system context, the same tidal heating mechanisms, and, in their subsurface oceans, broadly similar chemical environments. Results from Enceladus strengthen the prior probability that Saturn's ocean moons are chemically active in ways relevant to habitability. The fifth development is the September 2025 NASA announcement about possible building blocks of life on Titan. The NASA announcement, based on the July 2025 Mayer and Nixon protocell paper, described how Titan's alien lakes may be creating primitive cells through the amphiphile vesicle mechanism. This was the highest profile official communication about Titan's prebiotic chemistry in years, and it significantly elevated the scientific community's awareness of the protocell mechanism. The research is ongoing. Laboratory experiments to verify the proposed vesicle formation mechanism under Titan-like conditions are in progress at several institutions. The next decade of Titan science will be defined by preparation for Dragonfly and by what Dragonfly finds when it arrives. The preparation is already underway. Laboratory experiments on tholin chemistry are proceeding at NASA, at JPL, and at multiple university research groups. The goal is to understand, as precisely as possible, what chemistry Titan's atmospheric organic synthesis produces under realistic conditions, so that Dragonfly's measurements can be interpreted correctly. If Dragonfly finds glycine at Selk crater, scientists need to know whether that glycine is consistent with impact chemistry, with prebiotic synthesis, or with biological activity. The distinction requires knowing the background chemistry well enough to identify anomalies. Computational modeling of Titan's methane lake chemistry is advancing. The protocell mechanism proposed by Mayer and Nixon requires specific amphiphilic molecules to be present at the lake surface at sufficient abundance to form the bilayer vesicles they describe. Whether those molecules are present at the required concentrations, and whether the vesicle formation rate would be high enough to produce detectable structures, are questions that computational chemistry and laboratory experiments are beginning to address. The Dragonfly mission itself is the defining development. When Dragonfly launches in 2028, it will carry the most sensitive chemical analysis instruments ever sent to an outer solar system world. The Dragonfly mass spectrometer is capable of detecting amino acids, nucleobases, and other complex biomolecules at parts per billion concentrations in surface samples. The gamma ray and neutron spectrometer will map the elemental composition of the surface to depths of several meters. The seismometer will listen for evidence of internal activity, potentially detecting vibrations from the subsurface ocean or from cryovolcanic activity. When Dragonfly arrives at Titan in 2034, it will land first in the equatorial dune region, a landscape of organic dunes blown by Saturn's tidal winds, and begin its survey. Over the following years, it will fly progressively toward higher latitudes, sampling increasingly varied terrain, before reaching Selk Crater for its primary science observations. What it might find at each site is genuinely unknown. This is what makes Dragonfly so exciting and so significant. The mission is not going to Titan to confirm a specific hypothesis. It is going to Titan to see what is there, to take the first direct chemical measurements of a world whose chemistry has been studied only from a distance, and to find whatever there is to find. In the history of planetary exploration, there have been a handful of missions that were genuinely transformative, not because they confirmed what was expected, but because they found what was not. Viking on Mars, Voyager at the outer planets, Cassini at Saturn, Huygens on Titan's surface. Dragonfly has the potential to be another. The specific question it is equipped to begin answering, whether Titan's chemistry has crossed the threshold from prebiology to biology, or whether it remains a frozen record of the universe's capacity for organic complexity without the spark of life, is among the most profound questions in planetary science. And, beyond Dragonfly, the question of what comes next is already being discussed. A future mission to Titan's methane lakes, a boat, a submarine, a floating laboratory, could directly sample the chemistry of Ligeia Mare or Kraken Mare, the largest methane seas. If the protocell mechanism is real, a lake sample mission might be the instrument capable of detecting the vesicle structures directly. The Titan Ocean World Assessment Report, part of the most recent NASA Planetary Science Decadal Survey, specifically identified a future Titan Lake mission as a high-priority, long-term goal, and a future mission to probe Titan's subsurface ocean, analogous to the proposed Europa lander or an Enceladus plume sample mission, would directly test whether the water-based habitat beneath the ice hosts the kind of microbial life that the F-Holder biomass model suggests is physically possible. Titan is not a question that will be answered by Dragonfly alone. It will be answered over generations of exploration, with progressively more capable instruments, building on each other's results. Dragonfly is the first chapter of that investigation, and here is what makes the Titan story truly remarkable. Not the methane lakes, not the organic atmosphere, not even the protocell proposal or the subsurface ocean. What makes Titan remarkable is what it is forcing us to ask. For the entire history of astrobiology, the scientific study of life's potential beyond Earth, the search has been organized around one central assumption. Life requires water. Liquid water, specifically, at the right temperature and pressure, as the solvent in which biochemistry occurs. Every planet and moon that has received scientific attention as a potential habitat has been evaluated primarily on whether it has had, or could have liquid water. Mars for its ancient rivers, Europa for its subsurface ocean, Enceladus for its hydrothermal plumes. The habitable zones around other stars are defined by where liquid water is possible on a rocky surface. Water is the organizing principle of the search for life. Titan is the first world we have ever studied in detail that asks, what if that assumption is wrong? Not wrong, in the sense that water-based life doesn't exist, it clearly does, on Earth, in extraordinary abundance. But wrong, in the sense that water is the only possible solvent for life. Water is what life on Earth uses. It might not be what life elsewhere requires. It might be one solution to the problem of solvent-based biochemistry, the solution that early Earth found, and Titan's methane might be another. If that is true, the implications are staggering. The number of potentially habitable environments in the universe is not determined by where liquid water exists. It is determined by where any liquid solvent exists, combined with organic chemistry and energy. And liquid solvents are, it turns out, far more common in the universe than liquid water. Specifically, methane is liquid on Titan. Ethane is liquid on Titan. Ammonia could be liquid on other cold worlds. Sulfuric acid is liquid in the clouds of Venus. If life can use any solvent, the universe is almost certainly full of it. If life requires water specifically, the universe is almost certainly mostly empty. Titan is the test case. The world that, if it harbors life in methane, will have answered the deepest question in astrobiology, not with a discovery about one moon of Saturn, but with a statement about the nature of life itself. Let that sit for a moment. Huygens landed on Titan in 2005. In 2.5 hours, it transmitted enough data to transform our understanding of one of the most extraordinary worlds in the solar system. Cassini spent 13 years orbiting Saturn, flying past Titan more than 120 times, building a portrait of a world more complex and more chemically rich than anyone had imagined. And in 2034, Dragonfly will land and fly and sample, looking for whatever is there. We do not know what it will find. We know what it might find. And the fact that what it might find, life in methane, life that does not need water, life whose existence would redefine every assumption we have made about where to look for it in the universe, is a genuine scientific possibility rather than pure speculation. That is what Titan has done, not found life, made the question bigger. But there is one more piece to this story. Because Titan is not the only moon of Saturn that is making the case for life in the outer solar system. There is another one, smaller, more active, and in some ways more immediately compelling as a target for life detection. A moon whose subsurface ocean is not inferred from gravitational measurements and radar data, but displayed to the entire solar system through geysers that spray liquid water and organic molecules into space at hundreds of meters per second. A moon that Cassini actually flew through, that returned samples of, without landing, and found complex organic chemistry, molecular hydrogen, and the specific signatures of hydrothermal activity. That moon is Enceladus. And the question of whether its plumes are carrying signs of life into space, signs we could detect from a spacecraft that simply flies through them, is one of the most urgent and most achievable targets in the current search for life beyond Earth. That is next time. Tonight, we did not just learn about a moon of Saturn. We watched what happens when a world confronts the central assumption of an entire scientific field, and forces that field to ask whether the assumption was ever as solid as it seemed. We saw Huygens descending through Titan's orange atmosphere in January 2005. transmitting images of a surface covered in rounded river pebbles of water ice and dark organic material. We saw the scientists in Darmstadt looking at data from 1 billion kilometers away and saying, "This looks like early Earth." We traced the organic chemistry that Cassini found in Titan's atmosphere, tholins raining down on the surface, amino acid precursors forming from nitrogen and methane and ultraviolet light. The same Miller-Urey reactions that first demonstrated life's building blocks could form spontaneously, running at planetary scale in a world 2 billion years older than the experiment. We saw the methane lakes, the rivers, the dunes of organic sand, a complete hydrological cycle, in a molecule 40 degrees colder than dry ice, on the surface of a world where water is a rock. We saw the subsurface ocean, confirmed by Cassini's gravity measurements. Liquid water, deep and warm, in contact with a rocky core, potentially hydrothermal, potentially habitable, potentially home to something that uses chemistry we already understand. And we arrived at the question that Titan has been building toward for 20 years of exploration. Does life need water, or does it need a liquid solvent, and water is just the one we know? Dragonfly will begin to answer that question in 2034. We are 8 years from the data. Even with 2 decades of Cassini data, the picture of Titan's habitability is far from complete. We do not know whether Titan's methane lakes contain any chemistry that cannot be explained by abiotic processes. The hydrogen and acetylene depletions observed by Cassini are consistent with biological activity, but also with abiotic explanations that have not been ruled out. We do not know whether amphiphilic molecules are present in Titan's lakes at the concentrations required for the protocell mechanism proposed by Mayer and Nixon. The laboratory experiments needed to verify this are in progress, but not yet complete. We do not know how much organic material percolates from Titan's surface into the subsurface ocean, a quantity crucial for the biomass modeling of the subsurface habitat. The October 2024 methane crust study changes some of the thermal modeling, but the percolation question remains open. We do not know whether the amino acid synthesis that modeling predicts occurred at Selk crater actually occurred, or whether Dragonfly will find the predicted products preserved in the crater's floor. And we do not know, at the deepest level, whether methane can support biochemistry. That question is the frontier of theoretical and experimental chemistry. Dragonfly will not answer it directly, but it will provide data that constrains the answer more tightly than anything previously available. There are a few things worth taking from this story that go beyond Titan. The first is that assumptions in science have a lifespan. The assumption that life requires liquid water, reasonable, evidence-based, and enormously useful for organizing the search for life, is now being seriously questioned for the first time in the history of astrobiology. Not because evidence against it exists, but because a world has been found whose chemistry is rich enough and organized enough that the question can no longer be deferred. The second is that almost is a scientific category, not a consolation prize. Titan almost has everything life needs. The almost is not a disappointment, it is the most interesting scientific datum available. It forces the question of what everything actually means. It forces the question of whether the missing thing is truly required or merely conventional. The third is that planetary exploration generates discoveries that reshape fundamental frameworks. The discovery that Titan has 2 potential habitats, a methane chemistry surface world and a water chemistry subsurface ocean, was not anticipated before Cassini. The protocell proposal was not anticipated before the tholin chemistry was understood in detail. The insulating methane crust was not known before the 2024 study. Each of these results came from looking carefully at a world that nobody fully understood, and finding something that nobody fully expected. The fourth is that prebiotic chemistry is not a historical curiosity. Titan is showing us what early Earth might have looked like chemically, in a world where the biological transition has either not yet occurred, or occurred in a form we do not recognize, or occurred in a place we cannot yet reach. In any of these cases, the chemistry is informative about the conditions that preceded life, information that our own planet has long since destroyed. And the fifth is this. The most important scientific question is not, is there life on Titan? It is, does life require water? Titan is the first place where that question can be asked of something other than a thought experiment. Dragonfly is the first instrument that will be in a position to gather relevant data. The answer, when it comes, will be one of the most consequential in the history of science. So I want to leave you with a few questions tonight. If life on Titan were confirmed, life in methane, with no water, using chemistry we do not yet understand, what would that mean for the search for life elsewhere? Would it double the number of potentially habitable environments, triple it, expand it beyond any current estimate? And if life on Titan were ruled out, if Dragonfly finds only chemistry, nothing that crosses the threshold from prebiotic to biological, what would we learn from that? Is a negative result at Titan informative? Or is the organic chemistry so complex that only chemistry is itself a profound and interesting answer? And the deepest question, what does it say about us, about the kind of creatures we are, that we built a nuclear-powered flying laboratory, aimed it at a moon of Saturn 1 billion kilometers away, and told it to find out whether life requires water? Sit with that for a moment. It is the most generous question we have ever asked. If this story stayed with you, tell me in the comments, which moment was the one that pulled you in? Was it the Huygens landing, and the scientists in Darmstadt saying, "This looks like early Earth"? The methane lakes with their coastlines and rivers and wave-carved shores? The July 2025 protocell paper, membrane-bounded droplets forming in a methane sea? The realization at the end that Titan is not asking whether life exists there, but whether our definition of life is complete. I want to know. And if you want more stories like this, the search for life beyond Earth, told honestly and without the hype, subscribe to Galaxy Pulse. We go beyond the headlines every single time. I will see you in the next one. 1 billion kilometers from Earth, beneath an orange sky full of organic molecules, beside a sea of liquid methane, on the surface of a world older than Earth's oldest rocks, something may be happening. We do not know if it is life. We do not even know, yet, if life is possible without water. In 2034, we will begin to find out. That is enough to make the journey worth it.